We're going to cover some very basic material on solutions and solubility. When making solutions, we want to know how concentrated they are. Concentration tells us how much solute has been dissolved. The unit that we use is molarity. It means moles of solute over liters of solution. The symbol used is a capital M, and it is read molar. So 1 M is read 1 molar. It means 1 mole of solute in 1 liter of solution. There are infinite ratios that would give us a 1 molar solution. Half a mole of solute in half a liter of solution, 2 moles of solute in 2 liters of solution, and so on. Molarity is moles of solute, that's the substance being dissolved, divided by the liters of solution. The solution is the total combined volume of the solute and the solvent. In order to determine how many grams of sodium chloride we need to make half a liter of a 0.25 molar sodium chloride solution, we start with the volume, 0.5 liters. We then use the molarity, 0.25 molar, as a conversion factor. 0.25 moles in 1 liter is what 0.25 molar means. Once we've converted to moles, we then convert to grams using the molar mass of sodium chloride. The answer, 7.3 grams of sodium chloride, tells us that if we put 7.35 grams of sodium chloride in 0.5 liters of solution, we will have made a 0.25 molar sodium chloride solution. To find the molarity of a 250 milliliter solution containing 10 grams of sodium fluoride, we first convert the 10 grams of sodium fluoride to moles using the molar mass. We then take the moles, 0.238, and divide by the volume in liters. 250 milliliters is 0.25 liters, and we get the molarity, 0.95 molar sodium fluoride solution. Often we have a solution that's already prepared, and we want to dilute it to make a different concentration. To do this, we take a simple equation, molarity of the initial times volume of the initial concentration is going to be equivalent to molarity of the final times volume of the final solution. In diluting a solution, you don't change the moles that you originally placed in the container. So the initial moles will be equal to the final moles, and molarity times volume is equivalent to moles. So by taking the equation M1V1 equals M2V2, we are able to solve a simple dilution problem. For example, how many milliliters of 6 molar HCl will be needed to make 1 liter of a 0.1 molar HCl solution? We don't know the volume of 6 molar that we're going to need to use. That's why we have the variable V. We set the initial molarity and volume to the final molarity and volume, placing in the 0.1 molar times 1 liter for the final. Solving for V gives us 0.0167 liters or 16.67 milliliters. The volume units are not important. You can use any volume unit you want. They simply need to agree so that they can cancel out. What is the new molarity of a solution that is made by diluting 250 mils of a 0.5 molar HCl solution to 400 milliliters? Using the same equation, we take the initial conditions, 0.5 molar, 250 milliliters, and set them equal to the final scenario, which is 400 milliliters times the new molarity. In doing this, the new molarity will be equivalent to 0.31 molar. It's important that your volume units, again, are equivalent to each other so that they can cancel out. Here's another sample problem. What volume of 12 molar HCl is needed to prepare 300 milliliters of a 2.5 molar solution? The original conditions, 12 molar, unknown volume, are set to the new conditions of 2.5 molar, 300 milliliters. The volume is 62.5 milliliters. What this means is if we pull out 62.5 milliliters of our original 12 molar solution and dilute it to a volume of 300 milliliters, we will have prepared a 2.5 molar solution of hydrochloric acid. Adding any solute to a solvent will lower its freezing point and raise its boiling point. The compound that you add must be soluble, but if the compound is soluble in the solvent, then you will definitely lower its freezing point and raise its boiling point. So adding salt or any soluble compound to water will always lower water's freezing point below 0 degrees Celsius and raise its boiling point above 100 degrees Celsius. The reason that the solute lowers the freezing point is that it interferes with the formation of the crystal structure of water. The solute actually gets in the way of water forming its six-sided crystal structure. Water then needs to lower its temperature in order to freeze at a new lower temperature. Salting the roads lowers the freezing point of water. If it's not cold enough outside to refreeze the water, then essentially it melts on the roadways. Solutes interfere with the boiling of water because they interfere with the vapor pressure of the liquid. You actually need to get the temperature higher in order for pockets of vapor to form, so you have an increase in the boiling point. The antifreeze in the radiator keeps the water in the radiator from both freezing and boiling over by lowering the freezing point and raising the boiling point of the water in the radiator. The more particles there are, the greater this effect on freezing and boiling point will be. For sodium chloride, when it dissolves, it forms two particles, sodium ion and chloride ion. When calcium chloride dissolves, there are actually three particles, two chloride ions and a calcium ion. For calcium phosphate, there are three calcium ions and two phosphate ions, for a total of 5 ions. Calcium phosphate would be much more effective at lowering the freezing point and raising the boiling point. When you look at C12H22O11, you might expect a lot of ions to form. But remember, C12H22O11 is not an ionic compound. So actually, there's no ion formation. There's only the one molecule, so it would be the least effective of these at raising the boiling point and lowering the freezing point. The properties of raising and lowering freezing points are called colligative properties.